Okay. So, week 8, I think. Yeah, we're on week 8 here. It's going to be our typical week. We have lab this week, which is going to be our Atterberg lab. Saying bring your patients for this lab. If you're not familiar with Atterberg's, oh my gosh, we have the Shikriya mob coming in here. Right? Okay. So we have a typical week. We have our lab. Your homework too is going to be due on Sunday, so just please keep that in mind. And then we will have a quiz this week. As you know, this is kind of that last regular week. I know for a lot of you guys with AC, it's not a regular week. But after this, it's going to get a little hectic. So please stay up to date with Canvas, put the notifications on, whatever you have to do to pay attention with the announcements and the drops when it comes to assignments. So as I said just previously, we're just going to have one compaction lecture today, and then lecture in situ stress will actually be on Thursday, so we'll have that on the 27th, and then we'll do a video lecture next week on the 4th, and then potentially we'll be able to cut one of these video lectures out. But from now on, the next 3 lectures after this Thursday are going to be video lectures, and then we have our spring break. So yeah, I will still be able to communicate, email, Canvas, Teams, whatever you need to, just you can send me a message. I'll get back as soon as I can. But office hours will be virtual as well, just with the travel and everything. Your lab number 4 reports, I will make the assignment. That will be due Friday, 2025, this coming Friday. And I promise you, I'm going to get started grading. I'm sorry. I know it's been a delay. My Canvas thing is already like triple digits notifications. So I have some time on the calendar tomorrow to start grading that. Yeah. So, Peter.
Will it still be weekly quizzes? Yeah. Video lecture.
As long as we have lectures, then yes. Yeah. So you can kind of see you have like the theme coming up, the next topic. So we'll have a weekly quiz on in situ stress. And then we'll have a weekly quiz on the subsurface. So there's going to be at least those 2 quizzes.
So for the institute, since it's the second lecture is on that Monday, or not, the Tuesday, would our quiz be on that Tuesday?
No, the quizzes will still be due on Friday. So what will most likely happen with the compaction quiz, or this Friday's quiz will only be on today's lecture. And then next week's quiz will be on Thursday and Monday's lecture. So it'll be more like topical quizzes rather than like weekly quizzes. If that makes sense. So yeah, I will make next week's quiz too. I will make that available after class on Tuesday. So those traveling for ASCE can knock it out before Friday. Don't have to worry about doing that. Or everyone's going to be in a hotel. Just have a big, quiz party. That's what you guys want to do when you're on conference, right? Work on homework and quizzes. That's the only thing too.
That's Western.
Their Wi-Fi might be out.
Yeah. I don't think they get Wi-Fi. Those parts. Okay. All right. So we're going to be talking about an important concept today, compaction. And did Dr. Islam touch on this at all in CE materials?
Yeah.
Yeah, probably.
Well, if you did, then he did.
Okay, well, cool. I usually touch on this in CE materials, so but I can't remember, things can get going kind of quick and maybe you forgot to do this. So some of this might be recap and maybe they'll be jogging your memory as we talk about it. But it is important, you guys will probably make sense why, like this is a big area when it comes to ground improvement and then also using soil as a material. So bringing in soil for fill or for roadway embankment or for an earth embankment of any type, using it as a substitute as a construction material, we're going to need to compact it using different types of devices and ensure that we're meeting the strength criteria that we're designing for against. So last week, what we were talking about was site investigation. And the whole goal of the site investigation using the SPT, which stands for what? Standard penetration test, and then the cone penetration test, or CPT. The whole goal of this is to find these design parameters. So we find these design parameters or soil properties that then give us some insight on how the soil can be used for whatever. Like, so when it comes to soil strength, when it comes to soil compressibility, or even when it comes to the soil permeability. So all of these are parameters that are, the soil has, like certain soil has different behavior for. So much like how like when we make steel or when we make concrete, we can choose the compressive strength based off of the cement type, right? We can choose the steel type or the yield strength or the tensile strength of steel based off of the grade of steel that we're using. So with those chosen materials, with soil, we have to determine what those parameters are using these testing techniques. So it's more so like we're finding out what the site is giving us rather than us choosing the material itself. Now, if any of these cases, if the site is not ideal, like so, if we need to modify the strength or modify the compressibility or modify the permeability, then what we can do is use soil compaction or what we also call ground improvement. So this is like a way of ground improvement as well. So we've all seen types of soil compaction and we'll get through those different types today. But essentially what we're doing with soil compaction is increasing the soil density to achieve these desirable parameters, whatever one that is. And we do this by applying mechanical energy. So we're taking these big devices, we're applying energy, and that energy is then removing the air voids or causing the soil to densify such that we can achieve whatever strength we want, whatever permeability we want, whatever like material we want. So soil compaction has a wide range of options from just a very simple, like even just a hand tamping tool, to like a plate compactor like this. Probably most common is the vibratory rollers that we all see on the side of 295. We also have different types called sheep's foot rollers, which we'll talk about when these are used for. Impact rollers, which are more like pull behind. And even different types like deep dynamic compaction. Deep dynamic compaction, we'll talk a little bit more, and I'll show a video here in a little bit. This is achieving, you're essentially lifting a massive weight and then just letting this weight fall and then that hit the ground, and then you are transferring energy to a much deeper depth. And so this is used when you need to improve soil layers up to like 30 meters or 10 meters in depth or so. And it's pretty effective, but obviously you wouldn't use plate compactors. We see kind of a trend of increasing energy, but then also soil types and different applications for each one. Now, on a geotech perspective, like you would be working heavily with the GC or the contractor in this case. But this is one of those information still where like you need to know as a geotech the different applications of these types of compaction so you can choose the contractor correctly, or you can just double check and also not sound stupid. So it's one of those things where this might not be exactly in the wheelhouse of a geotech, or it might not be under the direct responsibility of the geotechnical engineer, but it's at least within the realm of our work scope. So with the different types of soil, like gravel, sand, silt, clay, and domestic waste, all of these types of conditions are going to have different applications. So, for example, the static sheep foot roller. Has anyone seen these before? Okay, we don't really see them too often in Florida. They're mainly used for clay. So they're going to be very good in clay soils. So if you drive up in Georgia and stuff, the DOTs up there, they're going to be running these sheep's foot rollers. And the reason why is because, like, as we talked about with clay, with the SPT, clays are sensitive, like little structures of soil, right? And if we take a hammer and hit it, then it's going to just disperse it everywhere. So this sheep's foot roller kind of kneads the clay into densifying it, instead of having a smooth cylinder where the clay might stick to it, or an impact where it's just going to smush it around. So these are very good for clay. This is also used a lot in domestic waste just because of the variability of material, like for landfills and different types of applications like that, as well as for silty soils. But it'd be kind of poor for gravel and sand. I wasn't showing, I didn't clap everything. Okay. Our vibratory cylindrical rollers, this is the most common one for roadway subgrade preparation, which means our sand and our gravel. These are going to be the go-to ones here. So these are very good. Where our silts, clays, and domestic waste will not really be applicable for it. And the silt and the clay is just going to kind of stick to it. Domestic waste is going to have a hard time pushing everything down or gaining traction on it. For the impact rollers, this is good for gravel. It's also used pretty well in domestic waste or for landfills. Let's say like a medium or a like a little question mark, maybe for clay. Depending on the cases of clay, you could use this. But for silt, usually it's not cohesive enough that it's just going to sink through it. And then the sand is also good in this case. Now for a deep dynamic compaction, this is where the domestic waste, very good. So we'll see, this is a good way to compact mine tailings. We use deep dynamic compaction a lot over in like Polk County, where they have all the phosphate mine tailings, as well as site prep for old landfills that are now capped and just compressed out. So to get to a much deeper depth. You obviously do not want to use this in clay because it's just going to get stuck and splash everywhere. Also pretty poor for medium. Then it's good. It's good. So the way we have to think about this is when we are applying energy to soil, what really we're applying energy to is the water in the soil. So it's kind of a tricky thing at first that we will cover in a lot more detail when you take advanced design analysis foundations, or if you take that with me next semester. But when we apply energy to water or energy to soil, what happens is that energy is going to transfer directly to the water within the pore space. And so we need to think of this as how easy is the water going to leave these soils? For clay or for gravel and for sand, it's very permeable. So water can leave the pore space pretty quickly. For silt and for clay, it holds and retains water. The permeability is really low. So as we apply energy to it, that water is not going to dissipate. Instead, the water is going to retain, and that's what causes it to splash around essentially. Because water has no void or no volume change, has a Poisson's ratio of 0.5. So that's why that's like the way of generally thinking with this is for things that are very highly permeable, we want to use something that applies a lot of energy. For something that is very low permeable, we need this static, like kneading action in it and applying energy smoothly over time instead of dynamically. So this video is kind of interesting. If it will actually load, maybe, or it already disappeared. Go. So this is a really interesting technique that if you ever get a chance in your career to actually go and work on in person, it's really fun just to go to a job site to see them lift this 12-ton or 10-ton mass into the air and then drop it strategically, especially if they have multiple cranes going at once. But this is used on a lot of large-scale geotechnical problems where you need ground improvement to a certain depth. So mine tailings, any loose, really like old riverbeds that they're trying to develop on. So for some dam work. And a few, there's only a few like specialty contractors like Menard or Keller Group that can like usually do these deep dynamic compactions. And it was working. As soon as I hit X, it'll probably load up again. Yeah, okay. Let's see if we can just play from here. Well, maybe this video is not going to work. All right, just close your eyes and imagine a sweet drone footage of just like going through a beautiful sunset and a bunch of weights falling and hitting the ground. That's it. I'll post the video. It's not too crazy, but it talks about the whole process of deep dynamic compaction and some of the applications of that. So why do we compact soil? So overall, it increases the strength of our soil. So what we'll learn and what the general theme of geotechnical engineering will be is granule soil will increase in strength as we increase density. So as we add more to our little cube, add more material, then there's more frictional resistance, there's more particles locking together, which will add against or will increase the strength. So this is really important for slope failure. So we would compact very strategically on embankments like this. To ensure against shear failure on slopes. It also will decrease compressibility, or essentially what it does is it accelerates any potential settlement or compressibility by causing the settlement to occur like on its own. So there's a lot of cases where if we know an issue will be an issue at the geotech at the site, like potentially in like 5 or 6 years or 10 years, like what they would do is induce that settlement ahead of time. So what before the project is complete, before it's connected to all the surrounding infrastructure, and compaction is a way of doing that. This will also decrease permeability. Just as a recap, the permeability is the ease of water to flow through the pore space. So decreasing permeability means it makes water travel through the soil at a slower rate, which is very important for dams. Like if we're making an earth dam or a levee system or any type of mine where we might have like a washing station, or you don't want that mine, the water to flow into your open cut. So it's very important, and you compact soil to achieve it that way. And it also helps, not so much in Florida, but control seasonal volume change. And so this is really important in areas like Texas, where we have shrink and swell clay, as well as frost heave. Has anyone driven in like the Northeast where you like see signs on the road that say like road may heave due to like snow or something? I don't know what it says exactly. I remember seeing it once in Vermont. But essentially, what if there is too much pore space in the soil, then water can intrude in it, and whenever that water freezes, it's going to heave the roadway up or heave the structure up. So what we can do is we can decrease that potential for void space by compacting the soil ahead of time, such that less water will intrude the soil in the pore space, less heat will occur. So the overall result is, as we compact soil, what we are doing is we are removing the air voids. So we are decreasing the air voids, which will in turn increase strength and density. I guess I should have it the other way around, density and strength. The benefit of that is. Benefit of compaction is. Generally an inexpensive. So if we have undesirable properties, it's a lot easier to go in and actually change those properties rather than to remove the existing soil and replace it, or to change your project location to where better properties are. So compaction can be likened to like admixtures in steel design, or admixtures in concrete or something, where like you might have certain issues that you need to achieve. And so we can add this additional step of ground improvement to meet that criteria that we need. So the general thing of soil compaction, what is happening? We have our beautiful phase diagrams. You remember that from a few weeks ago. We have solid water and air portion. So what we can only compact non-saturated soil. So we have to have air in it. If we compact saturated soil, then nothing is happening. We can't densify past 100% saturated soil. If you remember, there's that zero air void curve, that maximum density. So if we're already at saturated conditions, we can't compact any further. So this is for non-saturated soil. But what we do is we remove the air voids by compacting it, or by rearranging the solid portion such that some of the air voids are removed. So we're removing the total volume. So with each pass after more compaction, we're essentially removing the air voids. And then what we do is we replace those air voids with more solid material. So that's why when you see the rollers coming in or whatever at the job site, you see the sheep's foot rollers, or you see the vibratory rollers, you'll usually see a dump truck nearby with soil fill, and like a backhoe or a grader to come in, because you'll compact it and then you will put more soil in to meet that grade line. And essentially, I mean, on a road scale, that makes sense, but on like a soil like specific scale, what we're looking at is we are adding more mass to a set volume. So as we add more mass to a set volume, we're increasing our density. You have a question?
Can you compact something without using a compactor by just your plant? Because wouldn't the water push out the air and then then it would evaporate and it would just get replaced by air?
Isn't there a method where they just pile dirt on, just like make huge mounds of dirt?
Yeah, surcharging, that's a way of compacting clay that we'll talk about. I've never seen it just like jetting water. Like if that's what you're talking about, or using static, like the dead weight of water to compact it. I don't know. I've never seen either cases. I wouldn't think no, because like the whole goal is to remove air. So adding more water, yes, will work, but then you'll remove air, but you won't be removing the total volume. You know, the air will remove the total volume, which you can then replace with, or lower the total volume, which you can then replace with more solid material. If that makes sense. I don't know. I'll look into that. If I find something, I'll let you know. Maybe like pressure washer or yeah. So anyways, that's how this increases here. We're increasing our dry density, we're increasing our mass for the set volume. So the whole soil compaction theory is kind of interesting if anyone's interested in the history side of it. It really spawned out of the 1920s, 30s out in California, when they started having to build all these really large earth dams and reservoirs for the drinking system in the agricultural areas out in California, like right on the other side of the Sierra Nevada areas. I just think this dude's one has a really cool name, Dr. Proctor. And also just like, this is what geotechnical engineers looked like in the 1800s. Like, you know, I don't know what he's doing, but just a lot of field work. But he, one of the first projects that utilized this type of compaction and realizing like, hey, we can actually control soil to our advantage instead of just bringing in heavy rocks and boulders as a fill material or just bringing in concrete. So he developed this quantitative way of checking compaction, soil effort and using moisture content. And the first was applied for this Bouquet Canyon Dam, which I think is still out there in like central California area. But essentially he said that realize that the extent of compaction can depend on 4 things. So it depends on the dry unit weight, which is our gamma dry. It depends on the energy, or the compaction effort is what it's called. So this would be like the type of machine that we are able to apply to it, like how much energy we can physically apply to it. It depends on the soil type and the gradation. And then of course, the big thing is the water content. Now, did you guys do the Proctor hammer test in CE materials? Okay, yeah. So this is where he was named after, or it was named after this Proctor hammer. And that's what you guys should have like been able to see out of that lab was, okay, we look at the dry unit weight relationship with the moisture content, but then also how that relationship between dry unit weight and moisture content changes with the energy applied and changes with the soil type or the gradation type. So the whole theory is that we can apply this compaction effort in, or apply this compaction effort, which is the measure of mechanical energy. And it's actually something that we can calculate in terms of joules or whatever we measure energy in. And the benefit of that, as you remember back from the lab, is we can apply this same energy to our soil in the lab as we are applying in the field, because we normalize it by volume. We normalize it by the volume we're applying. So in the field, this is a function of the number of layers, the number of passes, the weight of the roller, or the technique. So there's all these handbooks and guidelines that like Caterpillar will produce, or whoever's doing the deep dynamic compaction, where you can get a quantifiable number of how we can change this device or how we can change the amount of energy in the field applied to our soil. And for the water content side of things, this is where the soil type comes into play a lot, because how the soil retains water is going to be dependent on the grain type. So we already talked about how clay retains water more than gravel does and more than sand does. So with the water content, you have this sweet spot or Goldilocks zone, where if we have too much water in our soil, then the water is going to transfer the energy away from the soil grain. And that's the whole thing I was saying before, where water has a Poisson's ratio of 0.5, which has no volume change. So think of a balloon, a water balloon that's tied. Like you push it on one side, it's just going to expand in the same direction, right? So like, even though you see change, like deformation, there's no total volume change. You're not losing any volume. So if that's the case, then when you apply this energy, it's just going to shove all the other sand particles or gravel particles out of the way. It's not going to rearrange them into a denser structure that will then increase the density. Now, if we don't have enough water, then the friction will actually overcome and it'll be difficult to apply energy, and it won't result in the movement of the actual grains. So in the lab, we do this theory here where we show the range of moisture content on the x-axis, and then the corresponding dry unit weight. And the dry unit weight is our compaction, because this is our density. So here we can see this relationship for this, what we call compaction curve. And here at this point, this is called our optimum moisture content, or the Goldilocks moisture content, where this is the moisture content that will produce the highest density. Now, this is just for one type of compaction energy. And so let's say we use a beefier machine or a bigger machine. What would produce, let's 2 times the amount of energy applied. What will happen is that curve will shift up and to the left. And I want you to think about that like physically. Hopefully that makes sense. Like what we're saying is with more energy, we can apply a higher density, which makes sense. And we can apply that higher density at less of a moisture content. Because remember, the moisture is there to allow like the particles to roll over, like essentially like lubricating the particles to allow them to roll over. So if we're applying more energy, we need less water because those particles are going to move regardless. So it's going to shift up to the left, and if we have more energy, then we see a higher density, and we see a lower optimum moisture content. So when it comes to like, well, why don't we just use the most amount of compaction energy then, and we can achieve the highest density in the field? Like, of course, like with this shift of line comes more work hours or more expensive equipment or whatever. So it's always this optimization. Maybe you don't need to achieve a super, super high energy. Or maybe in some cases, it's not the energy, or it's not the dry unit weight that's the limiting factor, it's the moisture content. Maybe you're working in Arizona where you just can't work with, like, you know, you pour the water on the, you take the spray water trucks out and it just like evaporates right away. So maybe you have to adapt your energy to account for the fact that your moisture contents are going to be in a lower range anyways. So it's this like kind of 3 variable system that you have to optimize depending on your site conditions, or depending on, you know, your requirements for the project that you're constructing. So what we see is like with the same soil or the same gradation, then the curve should theoretically look the same. It would just shift up and to the left. So that's what this is showing here. And then if you remember from that one lab, what we also plot here is the zero void curve, or the gamma ZAV. And that's the saturated curve. So that's essentially saying at this curve, this is the density where the soil is 100% saturated. And if the soil is 100% saturated, then there's no air voids to remove. So we can't increase the density at all because it's already at its maximum density. The only way we could do that is to remove the water or to add more soil to it, which is not what compaction can do. That's when we get into surcharging and stuff, which we'll talk about later. Right? So usually what we'll see is that there's a this curve. If we're using the same type of soil and we're only changing the energy, we'll see this line of optimum moisture content, or just line of optimum is what I don't know how to spell optimum. Whatever, I think that's close enough. OPTI scribble. But you have this line, it's almost like a function that is just going to tell us how, as we change energy, then we see the dry unit weight and the moisture content change. So let's remember, this is for same soil or same gradation. So this is a chart that shows how the soil type will change the optimum moisture curve. And so these are 8 different soil types. Your 1 and your 2 and your 3s, these are the sandy soils. And then your 4, 5, 6, and 7, these are our more clay or fine grained soils. So what do you notice as we go from like well-graded silty soils here to like clay soils? Like, what do you notice about the shape, not the location here? not the location on the chart, but the shape.
But
Yeah, essentially it's less sawtoothy, right? It mellows out the curve a little bit, which could be a little difficult because it's harder to identify that line of optimum. Like, so for well-graded soil, or soil that has a good mixture of densities, then we see these sharper patterns. So it's easier to discern those high points. And you can see down here at the very bottom, SP, poorly graded sand, this is one of the most flattest ones. So for poorly graded, that means the material is basically all the same size, not all the same size, but it's not a well-distributed range of particles. So, I mean, you have a bunch of ping pong balls, like you're gonna apply energy to it. You're gonna rearrange them, but it's not gonna change the density much, you know? So like the whole compaction process is applying it. So the finer grain particles will then find the nooks and crannies of the larger grain particles and settle in and decrease the air voids that way. So mainly these coarse grain soils, they're going to be affected by gravity. So that's why they can be achieved, or they can achieve a little bit more of a compaction. The fine grain soils, they're affected more so by the moisture. So you see these wider moisture ranges, like you see for the clays here. Less of a sawtooth. And a rule of thumb, again, if we were to plot the zero air void curve, then all the data should be to the left of this, because this zero air void curve is essentially that maximum potential dry density. So if we have any data on the right side or above that curve, then there's an error somewhere in our calculations or our measurements. All right, so let's talk a little bit about the standard Proctor compaction test, and sounds like you guys did this already, so hopefully this is just a refresh, most of it. So the whole goal of this thing is this was developed to simulate compaction in the lab. So instead of having trial and error out in the field and mobilizing the contractors and the equipment and all this stuff, we can apply that same energy that we need out in the field in our nice climate controlled laboratory where we're paying an intern $20 an hour to do it instead of millions of dollars out in the field. So it's a lot better for the wallet that this exists. We save a lot of money. So the whole purpose of this is to find the optimum moisture content at which the maximum dry unit weight is attained, but for specifically the energy that is needed in the field. So this also allows us to answer the question, like, can we achieve this with the material, with the equipment we have in the field? Like, can we even get this moisture content? Like, if we do this in the lab and we're saying, oh yeah, the optimal moisture content is 80%. But again, you're in Arizona or like, you know, Nevada in the middle of the summer, like, it's like, okay, no, we need to boost up our energy because we cannot achieve a moisture content that high in, you know, during our construction month or whatever it is. So it allows engineers to do the trial and error in the lab and not in the field. When I say field, I always just mean at the project site where time is money and all that stuff. And the lab compaction effort in the Proctor mold can be compared to the field compaction effort from the Caterpillar machines or whatever we're using. So that's how we can compare those two. We normalize it based off of volume here in the lab, which allows us to then scale it to our field. And you get the Caterpillar handbook and you see what exactly you need, what type of dozer, what type of machine you need to actually apply this energy to our site. So the standard Proctor compaction test, looks like this, except it from 2025, not 1990. But it's this giant steel bucket, the hammer, this is the standard Proctor hammer, so we also have the modified now to apply a little bit more energy. It's 5.5 pounds and it drops 12 inches, lift it up, drop it. This is the manual version, there are automatic ones too, but we make the students manual just for the build's character. And the whole thing is we can find the density from the mold by knowing the mass of the mold, right? The weight of the mold. The volume of the mold, we know, we can find that here. Then we use our oven to find the moisture content of the soil. And then once we find that, we can find our dry density, because this is going to be our moist density, technically. We can find our dry density by using this equation that we all love. We always show things in dry density because moisture content is going to change throughout the project, summer, all that stuff. So it's, even though we use moisture content in the moment, like for compaction, we know it could be changing the next day or next week. So the general steps of this, we can take the masses of all our materials, all our Proctor molds, fill it with a material at a set moisture state, and then compact it using a standard method. So a certain amount of drops and a certain amount of height. And that's all just to ensure that we're applying the same amount of energy each time. And we do the different amount of trials, finding different moisture contents. And then when we calculate the dry unit weight, then we can find the x-axis, or we can find the y-axis and plot and find that optimal moisture content versus the dry unit weight. Not 100% sure, but I think this is Dr. Crowley when he was like in high school. That's kind of like, I always think that. Don't quote me on that. I can't be 100%. So when we can plot this, the whole thing is this line of optimum is related to a function that then relates the moisture content, the energy, and then the maxed density that we can achieve. And the whole reason why we would do this is, again, these are the variables that we can control or that we need to find in the field. That's the benefit of producing this line of optimum. So in our class, what we do in the lab is just one moisture curve, right? But then if we were to do that whole thing again and do it with 25 blows per layer, or then 30 blows per layer, 50 blows per layer, we'd be able to produce this line of optimum. And then with this, by calculating all of these, you essentially get a three-dimensional relationship. So obviously you have moisture content versus dry unit weight, but imagine another axis coming out here where now we have energy. And so we can find any of these based off of the two of them that we have. So if moisture content is a limitation, but we can use whatever energy and density is whatever we need to do, then we can calculate the moisture content that would achieve those two things. So again, all of this stuff, the blows per layer, we can calculate this energy in the lab in the Proctor. Using this, so we normalize it by the volume of the mold. But all it is the weight of the hammer times the height of the hammer drop times the number of blows, and then times the number of layers. So we can change it by any of these layers or any of these values. So there's a lot of different optimizing. If you need to apply a certain energy, Maybe you just get a smaller Proctor mold, or maybe you get a heavier hammer or a drop height. As long as it's standardized and you can do the same thing for each one of these moisture content trials, then you can, you can toy with it any way you want. So we go to the site and we have our, or we start off in the lab. We do our moisture content, our optimal moisture content. We determine, we call the contractor in the field and they're like, okay, we need moisture content at this amount. We need to use this energy, and that should achieve this amount of density. That's nice on paper, but of course we still need to ensure or check the density when we get out to the field. So even though the theory is all there, we still need to make sure that we're doing a correct quality control or engineering inspection for this. So there's different ways to determine the field density, and we're going to go over one of them in the lab section in this class. The most common one, which I'm going to put first, is nuclear gauge method. This is a portable device. It looks like one of those spot cleaner like vacuum things that you buy at Publix or something, like those scrub it things. Kind of heavy. It's very heavy. And what it actually does is you will go to the site or the compacted area. You will drill a little hole or auger a little tiny hole in there. And it has a probe that actually emits out, I don't even know, some nuclear like radiation, some small amount of some type of isotope thing that the chemistry does know. I should probably know it. But it can correlate that signal of the radiation reflecting back to the sensor. And if you know the moisture content, then you can actually calculate the density from that. And it'll give you a spot check right away. So it's really beneficial that way because it's a very quick, you can just move, and it's a device that takes the measurement right away. Since it does have the word nuclear in it, and it does use like a heavy metal isotope, or so even if it's not like crazy, like whatever the harmful. I've seen Oppenheimer. I should know these things. I don't know. not the really deadly type of radiation, but since it does include radiation, you do have to get specialized training, and we are not allowed to use it at school. Blah blah blah. So that's why we don't go over it. The most common tried and true version aside from that is the sand cone method, the sand cone test, which is what we're going to be doing in lab 6, I believe. And this is one of my favorite like engineering labs because it's just like the most like tried and true like engineering, like low tech thing where it solves a really important problem at like no technology, just very basic, just using scales and using something with a known density. So essentially what it's doing is like we can find the density of something by filling the hole with something that is a known density, which sounds weird when I say it. But like if we have a material that has a known density, which is this special type of sand, and we go out to a project site and it is compacted, and we dig a hole and we take the mass of soil that it took to remove that hole or to create that hole. Then what we need to know is find the volume of that hole. And so what we can do is fill that hole with something with a known density to calculate the volume of that dug hole. We know the mass that it took to dig that hole. And so we divide it by the volume, and now we can get the density of it. I swear it'll make sense in the lab. But it's very basic. All you need to do is measure this material that has the set density, and then you need to take a couple mass measurements. So it's a little bit slower because you have to take these mass measurements and everything. And it's a little bit more intrusive because you actually have to dig like a little, like 6-inch diameter hole. But it's still used like very common because it's very low tech. There's other types of methods like the pressure meter method, where it's correlated to density, but it doesn't measure it directly. So when we go to the field, we are not looking for this maximum or optimum dry unit weight. Because it's really unrealistic if you think about it. Like if we have like this relationship in the lab, how realistic is it that in the field we can actually achieve this 100% dry condition? It's going to be really difficult. So it's unrealistic to achieve this max or optimum. In the field. So typically what there is there's an accepted range of criteria based on the project's sensitivity. When I say sensitivity, I mean like the importance of the project. Like if it's a brand new like medical cancer treatment like facility or something, it's probably going to have a pretty tight criteria because we can't experience any settlement or out of commission for it. If it's a road cutting through the middle of Union County, maybe they don't care as much, you know, that gets like one car a day. If it's 301 where you're getting a lot of car or a lot of logging and trucking companies, then yeah, that's probably going to be a little bit more tight too. So typically what we look for is about 90 to 95% of the max dry unit weight. So we get a range of this. So I'll show a graph here on the next page of how to illustrate this. But this is what we would call like our relative compaction. So we would look at relative compaction, which is our dry unit weight in the field or whatever it is that's measured or actual, divided by our dry unit weight that is the maximum from our lab. And of course, we show it by 100%. So that's what we're saying by like 90 to 95% relative compaction. So it's just that. Like if we know our max is 110 pounds per square cubic foot, then 95% of that would be 0.95 times that. So graphically, it would look like this. So this is a little example here. So let's say our optimum moisture content's at 16%, and we're at 1.74 megagrams per cubic meter. That's our dry density. So that's right here. This is our peak. And we tell our contractor friend, okay, we need this at 1.74 megagrams per cubic meter. They're going to laugh at us. They're going to say, no, give me a range. And so we would say, all right, let's say the acceptable range for this is 95%. So really what we would look for is, as long as our dry density is greater than 1.65 megagrams per cubic meter, then we're within that accepted criteria. So that would be this range here. So then the question would be, okay, like, yes, so anywhere here, it could be here at this moisture content, but also maybe we want to go on the other side and have a more like wet condition here. So this is where we can have this range of moisture contents on either side of our optimum moisture content to apply. But we would have what's called considered wet of optimum and then dry of optimum. So there's two kind of cases that we can get, even if we have the same density. And that's just the way density works here with the bell curve of it. So even though our optimum moisture content is 16, the range of it, whether we're wet of optimum or dry of optimum, it will make a difference on the total amount. Does anyone want to guess which one is better? Wet of optimum? Who thinks dry of optimum is better? The answer is neither. It all depends. That's the answer for all of engineering. It depends. It's always depends. Really though, it's always depends. And I'll show you it here too. So this is kind of a rule of thumb when it comes to some of the beneficial properties of, you can see the two columns, dry of optimum versus wet of optimum. So for particle arrangement, for if we care about particle structure, then wet of optimum is better. So for you guys who thought wet of optimum, you were probably on the right track thinking wise, because what will eventually happen is the water will like evaporate or lose itself, and then those particles will settle and structure a little bit better. So if we're wet of optimum, then the particle arrangement is going to be a little bit more orderly. But if we want to get a more, like better, higher magnitude of permeability, then we want to go dry at the optimum. For compressibility, if we want to consolidate the soil faster, rapid consolidation, then we want to go dry of optimum or wet of optimum. So I kind of highlighted these here color wise with like what is generally a good thing in engineering versus a bad thing in engineering. And you can see like it's pretty flip-flop. So it really is dependent on the application that you need, what you're trying to control. Because remember what we said, the things you can control, permeability, compressibility, and strength. Some projects you would want to control permeability over strength. Or some projects you want to control compressibility or how much it's going to settle over strength. That's what makes geotechnical engineering foundation design so interesting, is that like you have to first determine what is going to be the controllable issue or what is going to be the weakest link of your project. Like, and which going to fail first. And that's the thing you have to design according to. And that's going to change based off of the geologic conditions and all of that here too. So this is just a small like taste of wet of optimum, dry of optimum. Each like contractor might prefer to work in a certain way. So keep that in mind if you ever get to the point when you're working and you have to like work on a roadway project and the DOT is saying we need 98% compaction, and then you send out the report and you say like, okay, this based off of the soil type that we're using, it's going to have this range of optimum moisture content. And then the contractor calls you back and says, hey, I like working this way, you know, like don't be alarmed. Some of them would prefer using dry or optimum just based off of their equipment and their expertise in the area and the climate that we're working. So was this recap for the most part or brand new stuff? Brand new? Sure. Well, I'm glad we talked about it then, because I wasn't sure if he covered it. I wasn't going to talk about it at first, but anyways, we'll illustrate this a little bit more in lab 6. I know that's a few weeks from now for the sand cone test. But that's all I wanted to cover on compaction, at least from theoretical standpoint. And once we go over the optimum moisture content stuff, then you will need to know how to like find the optimum moisture content and calculate that on your exam too, like from your lab stuff. So make sure you know the concepts of where each, like the application of each compaction device, like where it's beneficial for, and then also the optimum moisture content, like how to find that. But that's it for that. Look at that, we're finished.
I didn't talk to Megan yet. You don't want to stay